My name is Aleksandrs Timofeev, and I am CEO of Polyant Technology. We are focusing on development of a new neuromorphic hardware. And what is the problem we solved? Look around, in new IoT era, the billions of sensors generate digital data tsunami. And we need solution to move data processing directly to on sensor level, like biosensor, like our brain and eyes do this. This problem is critical for IoT wearables and autonomous devices, and few digital neuromorphic accelerator perfectly work on data centers level, but it's still a problem to support neuromorphic data processing on tiny AI level, especially if you need always on and real-time application support. And analog neuromorphic solution can be work perfectly in that level, but still available practical solution, the ready product today. And we introduce neuromorphic analog signal processor. That is a new platform to make analog neuromorphic in practical reality today in various products. What is the core of our technology? What is the idea? We use fundamental property of deep neural net training. After a few hundreds of thousands cycles of training, the 90% approximately of neural net layers are become frozen. Just the final layer is still updated for classification. And the reduced data vector between fixed and flexible part is called as embeddings. It's 1,000 times less than input vector size. So we use this property to use our own EDA platform, and we do conversion of any trained neural net to our own proprietary format, and then to use analog single neuron for physical design of neural core. So that this is direct generation GDS files from digital neural net to chip layout. And we represent neurons as analog blocks and weights as a resistors array. And that analog structure, analog neuromorphic structure, it's 100 times more energy efficient than the digital core with the same data flow up to microwatt level power consumption in real-time data processing. And that is focused on, again, to sensor level data pre-processing, not for brain functionality for that. And that give us a very high efficiency and this tiny AI application. I just want to explain the one of the application where we can use this NASP core, that is predictive maintenance data pre-processing. For predictive maintenance industry now try to switch for wireless sensor node, but the biggest barrier here is a huge data transfer, because vibration, raw data, sensor generate megabytes per second data. If we use our concept to convert pre-processing core to analog neuromorphic chip, to NASP core, and shift data pre-processing to sensor level, we can dramatically reduce data transfer up to 1,000 times. That's what I mean before on embeddings description. So we can use only embeddings for machine learning cycle. So we keep the same idea of machine learning cycle. We have a cloud-based classification layer in digital environment, but we reduce dramatically data flow. So with pre-processing, it shifts to ultra-low power neuromorphic analog core directly on sensor, and just few kilobytes of data transfer to classification head in small model of neural net based on digital cloud. That open a lot of opportunities, enabling technology for energy harvesting sensor nodes. We can offer for industry AI sensor node with dramatically lower cost using low power network communication like LoRa or others. So it's an open wide range of new applications, not only high-end application like today in airspace or energy, but also for fleet management and can generate a new ecosystem of predictive maintenance for industry where don't use before that technology. So that is a summary of benefits of this solution. We can, again, using our ultra low power analog neuromorphic core, we can support full up to 20 kilohertz bandwidth of input signal, which is today it's not possible for digital system because the data flow is too high. And we can work in approximately below 100 microwatt power consumption, including data transfer. So that is possible for energy harvesting technology and use any IoT wireless communication technology. So that is an example of practical implementation of analog neuromorphic core that is not a lab. So our platform works. We already built first engineering chip, and that product chip, VibroSense, will be available, I hope, in second part in next year. So that is what we're doing.
Thank you so much, Aleksandr. Thank you so much for your interesting talk and showing us some of the nice works that is happening. So maybe one question that probably Paul Ditterer gave away at the very beginning of your talk was, how many synapses could you implement on this particular chip?
And that chip is approximately, we are not operate synapses, but they consist of approximately 50,000 of physical neurons and a few millions parameters.
Got it, got it. Okay, so maybe there aren't any questions, and since we have one question for one, time for one question, maybe I can ask something that I was wondering about is, are you also trying to think of a technology to, because you're talking about this agnostic to wireless communication technology, are you thinking about how you can look into sparsity from these computations in general and try to have sensors, these wireless sensors that can take advantage of it while you are, of course, you are saying it's agnostic, but still, do you think that can be a more whole-ended solution if you look into the sensor and the wireless side of things and look into the sparsity of it?
It's application-specific standard product. So we create the few lines of product which is focused for sensor type. First, it's a piezo sensor for vibration signal. Next product, it's focused for more medical sensor like PPG and other medical device for wearables. The third line, it's a voice processing. For we can take any type of microphone, MEMS, analog, or everything about voice processing. So it's a separate lines of product because your model and neural net for voice processing, for example, it's require different training and different expertise. So we create platform which can convert digital model to analog neuromorphic core. And then we cooperate with different partners who have experience in various neural net. So we have today 3 lines of partners, and we're open, so we can convert any type with no limitation, any type of convolutional, recurrent, any type of neural net.
Got it, got it. Thank you so much.